Okay, so we have this person here who is pulling a crate from rest, and that's getting dragged across the floor with friction. So if it initially starts at rest and then begins to move, we know that it's going to accelerate across the floor. Our change in velocity or the direction of our acceleration will be to the left. The earth pulls down on it, the rope pulls it, the floor supports it, and there's also a frictional force involved. So in drawing a force diagram, we have our object here. I'm going to call up positive y and to the left positive x. The reason I'm calling left positive x is because that's the direction of the acceleration. Kind of makes it simple. So you have the earth pulling down with a specific force. You have friction opposing the motion, friction of the floor on the crate itself. You have the rope pulling up at an angle at 30 degrees. Drawing the force of the rope here on the object and 30 degrees. And then you have the floor, which is pushing up, but not as much as the earth pulls down. That is because part of the rope pulls in two directions. It pulls left and up. So you will have the floor that pushes up, but it will not be the same as that of the earth because the rope partially pulls up. So we're going to actually also draw in the two components, the horizontal component of the rope and the vertical component of the rope. So we'll call this Ry and rope in the x direction. Now, before we set up Newton's second law, what I would like to do is I would like to express Rx and Ry in terms of the force of the rope itself in 30 degrees. So since we have 30 degrees here, opposite of that is going to be the rope in the y direction divided by the force of the rope in general is equal to the sine of 30 degrees. So the force of the rope in the y direction will equal the force of the rope times sine of 30 degrees. All right, remember sine and cosine are less than 1, so whatever the rope is, it's going to be smaller than that value. For the x direction, we're going to do force of the rope in the x direction divided by force of the rope is equal to cosine of 30. So the force of the rope in the x direction will equal the force of the rope times cosine of 30. Now that we have pretty much everything in its component form, we are going to apply Newton's second law. So we have in the y direction, we have the sum of the forces over the mass is equal to the acceleration. But we can see clearly that our acceleration arrow in our motion diagram points to the left, which means the acceleration in the y direction, it's not accelerating in the y direction, so it would be 0. So our equation would look like the following. We have two forces here that are exerted up. Okay, we have the force of the floor pushing up and the force of the rope in the y direction. And we have one force down, the force of the earth. So on the y-axis, we have three forces, which means three forces will go into the net force part of the equation. So we have the force of the rope times sine of 30 plus the force of the floor minus the force of the earth on the object. All divided by the mass is equal to 0. Horizontally, we have two forces exerted. We have the rope in the x direction, and we have friction in the negative x direction. So the acceleration, which will be to the left, is the force of the rope exerted in the x direction minus the frictional force of the floor on the object divided by the mass of the object. Okay, so a little bit later on, they give us some values for all of this, and we will carry through and determine what those numbers are. So vertically speaking, we multiply through by the mass. We are left with 400 newtons times sine of 30 plus the force of the floor on the object minus 70 kilograms times 10 newtons per kilogram. All right, so this will be 200 newtons plus the force of the floor on the object minus 700 newtons. All of this is equal to 0, which means the floor itself will equal 500 newtons. Okay, and it is less than that of the earth because the rope is assisting on supporting the object on the floor, which means the floor doesn't have to push up as much if the rope wasn't pulling up at all. If the rope was just pulling to the side, then the floor would be equal to 700. But since it is not, it is now equal to 500. All right, so in the x direction, I should have put cosine here. So this should be ax is equal to the force of the rope times cosine of 30 minus friction. So this is ax is equal to the force of the rope, cosine of 30, minus friction of the floor on the object divided by the mass. So we are left with 400 times 0.866 minus 75 newtons, all divided by 70 kilograms. If we were to solve for the acceleration would equal it would equal 3.87 meters per second per second. And there you have it.